Welcome, ladies and gentlemen. Good morning. May I have your attention, please? Thank you. And so we've got our new seats today, and we've got our new cooperative learning groups. We'll get a chance to work in those a little bit later as we approximate definite integrals today using the trapezoidal rule. So we're going to look at a couple different approximations as we develop the concept of a definite integral. We're going to see what that is and how it relates to the derivatives that we've already studied so far this year. So a super exciting unit here. Unit 5 is probably my favorite unit because we get to take all that we've done so far with our derivatives, our shortcut rules, our limits, and we're going to combine them into integrals and antiderivatives. So this is one of my favorite units all year long. Firstly, I'd ask that you raise your hand if you did not get a red mark for today, the 18th. Everybody good? Okay, let's go ahead and get going. And so on your OTL number 1, your prerequisite skill review, you already did some distance traveled estimations using the graphs and descriptions for Caleb walking and so on and so forth. Let's go ahead and consider Jack's walk. And so for Jack's walk, walking the dog, obviously, we're given a velocity in feet per second versus time in seconds graph. And we're asked several things like, when is Jack speeding up? And so we know in order to be speeding up, our same criteria hold true. His velocity and acceleration must be the same sign. What graph are we looking at? Are we looking at position, velocity, or acceleration? Annika?
Velocity.
Velocity. And so if we're looking at velocity, then what about this graph? What about this graph tells us acceleration? Right? What quality of a velocity graph would tell us about acceleration? Paul?
When the velocity is increasing?
Yes, when positive velocity is increasing, right? And so the slope of my velocity graph indicates acceleration. I need velocity and acceleration to be the same sign. So I'm looking on this graph when my positive velocity is also increasing, and so that looks like it occurs on the time interval, what, 15 to 20 seconds? Is that the only time interval? So we'll go ahead and say on the time interval, and I'll just go ahead and use interval notation for efficiency. I'll say on the time interval 15 to 20 seconds. Raise your hand if you already had that. Good, thank you, hands down. And what would a justification be? We could say that B and A have the same sign. So my velocity and acceleration have the same signs. I think I'm going to add V's slope here. I think that's a nice little embellishment. So V's slope on this graph is acceleration. When is Jack slowing down, right? So when is Jack slowing down? Well, we need velocity and acceleration to be the opposite signs. And so we're talking about positive velocity with negative acceleration. And if acceleration is the slope of velocity, we're looking for negative slope velocity but positive velocity value. So where that looks like only one interval again, 5 to 11, is that right? So 5 to 11. And raise your hand if you had 5 to 11. So you have 5 to 11 already, good. And thank you. A justification for that again could be velocity, v of t, and acceleration, a of t, opposite signs. Awesome. When is Jack stopped? And so when is Jack stopped? Well, what did you get for that? Riley?
I don't think he stopped at any point in the graph.
I agree. What would it take for Jack to be stopped on this graph? What would we need to see? Brandon?
A velocity of 0.
And as we survey this interval, it appears that velocity never equals 0 on the provided time interval. And so never on this graph. So never on this interval. Thank you. Okay, what questions do you have on the first three? Old news, nice, slow warm-up today as we get ready for our big bad mother daddy unit of them all, unit 5, integrals. Now we get to do how far did Jack travel during the first 11 seconds. So we've seen if we take, right, a velocity versus time graph, and we calculate the area in between the velocity curve and the x-axis over a specified interval, then the area, right, represents the net change in position. In this case, for a positive velocity graph the entire time, it would be the distance traveled over that interval. And so during the first 11 seconds, we'll go ahead and start from time t equals 0 up until 11 seconds. and we can break up the area underneath the velocity graph, right? The velocity graph and the x-axis into shapes that we know. So you can do this a couple different ways. We can break this up into this first rectangle, blue cross-hatch rectangle, and we can break it up into this green rectangle if we wanted, right? We don't have to. Green. And then I think we need a little black polka dot triangle, yes? If I wasn't as uniform, we could even make those into maybe spots like a Holstein cow here in Wisconsin, but we'll have to make do with what we have. So here we go. Let's go ahead and do our area calculation. So we've got my area of the blue rectangle when combined with the area of my green rectangle, when combined with the area of my black polka dotted triangle, right? Should give me an approximation for the distance traveled during the first 11 seconds. So here we go. Blue looks like length, base times height. So what is that? 5 times 9 plus, oh gosh, 6 times 4, is that right? 6 times 4? Oh, my goodness. Plus 1/2 base times height. So 1/2, 6 times 5, is that right? 5? Awesome, blossom. We'll go ahead and combine those and get an approximation then for the distance traveled. So it looks like 45 square units plus 24 square units plus 1/2 of 6 is 3 times the 5 is 15. Put it all together, and what do we have? Oh goodness, 45, 15 is 60. 84, I'm thinking about 84. Raise your hand if you have the number 84. The number 84. Keep your hand up if you know the label. What would be an appropriate label on that? Right. Thanks, hands down. Allie? Feet? Awesome. And how did you get feet?
Because it's like the anti-derivative of velocity, so I'll be like displacement or distance.
Oh, so you're thinking in terms of the derivative of position is velocity. So if we're going back up to position from velocity, right, then we're not doing feet per second, we're now doing feet. We're not dividing over the x units, right? So it's just y units would be feet. Okay, excellent, I agree. Today we're going to consider my y-axis units multiplied by my x-axis units. And so if my y-axis units are the height in these rectangle and triangle calculations, my y-axis units are feet per second multiplied by my x-axis units. My x-axis units were seconds. What would be feet per second times seconds? Well, that would give me feet as well. And that's going to work regardless if we're dealing with a motion, a particle motion application like position to velocity acceleration. That'll work in general anytime we're dealing with now antiderivatives. And so we've got now a technique for handling those units, just as we got our units for rate of change by doing y units over x units. We'll get our units for area approximations by doing y units times x units. All right, let's go ahead and then take care of our homework check. At this time, we're going to do 2 separate checks. And so first, I want to review OTL only. So that's OTL number 9 from Unit 4. We're going to go ahead and put your related rates packet on top. So I did count to 13 then. So related rates packet on top. Put that over the book review and then staple it together. If you're already stapled, that's okay. Just make sure that you're giving yourself credit for those that you completed out of 33. That includes the entire related rates packet assignment. Divide, enter, multiply by 2. Little box or infinite canvas score nice and big on top, round to the nearest half point. Sophia?
What is that?
That's okay, so long as you do your infinite canvas score nice and big on top, and you include the related rates packet. There's staplers on the side activity table, and then one on the front here, if you guys need it. You guys want to start it? Well, once again, this is review OTL number 9 only, okay? Make sure that your name first and last, 2A, number 9 are clearly labeled. Infinite canvas score should be boxed nice and big. And please don't pass up any prerequisite skill review unit 5. Don't pass up, right? The related rates book problems, just fasten your review assignment with related rates packet.
Thank you.
Thank you for your help, front rowers. Savannah, Sophia is ready to pass that up. All right, go ahead and fasten the review then. Review. Front rowers, make sure they're facing the same direction. Thanks, you guys.
Oh, sorry, here's my.
Review only. Thank you. Review only.
The review.
Thank you. Review only. Review only. Thank you. Okay. Review only.
Sorry, I'm gonna be a little honest. Yeah, I guess it's an area on this. Yes. It was like a mosh. And do like
Thanks for your help, ladies and gentlemen. Next, I'd like for your Unit 5 OTL number 1. This includes our Intro to Unit 5 worksheet, our prerequisite skill review for Unit 5 on top, and then the book problems. Those 3 stapled together for a total of 6. Please go ahead and give yourself credit for those you completed. Out of 6, divide, enter, multiply by 2. If you stapled out of order, that's okay, so long as your name, first and last, right? 2A, number 1 clearly labeled, and you're giving yourself an infinite canvas score box, nice and big on top. Go ahead and pass those from the back to the front. I'll keep those separate from the review. Thanks for your help. I appreciate that. And Hayden, you can send your doubles up. That's fine. That one goes on that side. I mean, not that I'm super picky about it. Thank you, Paige. Are we good with number 1? Thanks, Michaela. Thank you, ladies and gentlemen. Okay. So at the end of our discussion, at the end of our Bellwork discussion, we saw how the units for my area approximation, right, could be gained by taking my y units, and multiplying them by my x-axis units. Okay, this can be a general strategy that allows us to handle things where our scenario is a little bit more unfamiliar than a velocity versus time graph. And so in general, my velocity, if we measure that, let's just say meters per second, and we had a graph, and then we had our time measured in seconds. Then as we continue to travel over the course of some time interval, we could get an approximation for the distance traveled on a particular time interval by finding the area in between my velocity graph and the x-axis over some time interval A to B. And to get the units on that area, right, we take our y units, in this case meters per second, and multiply them by my x-axis units, in this case seconds, and we'll be left with meters. Okay, and that was like our Bellwork, although we were doing with feet per second and seconds. I want to extend this beyond nice rectangles, right? Nice rectangles and triangles like for our Bellwork, and consider different rates and different shaped curves. Okay, we can still apply the same notion of units by taking our y-axis units multiplied by our x-axis units. In general, right, the definite integral represents a product, the product of a dependent variable multiplied by the independent variable. Much as the derivative rate of change units are gained by taking dependent variable units divided by independent variable units, the definite integral represents an accumulated change over an interval. And we can get the units by taking our dependent variable units times our independent variable units. Consider the case with the appliances at home, right? And so here you are, you're getting ready for school, you're snagging that Go-Gurt, right, on your way out. You cut the top, you try to peel the top off, right, so that you can get at all that tasty goo inside, and Oh no! All over the color coordinated outfit that you spent 45 plus minutes last night putting together, the ensemble, right? And now you've got to do a quick pat dry with the baby wipes. You know the one I'm talking about. Those wet ones work the best because they get the stain right out, but now it's all wet, and so you're going to go ahead and do it. You're going to throw it in the dryer. You turn that dryer on, and it requires electrical power. That's measured in kilowatts. And so we'll go ahead and label our vertical axis kilowatts. And as you're running that electrical dryer over a time interval, right, the 7 minutes that it takes, the 7 minutes that it takes is a portion of an hour, let's say, that our x-axis is labeled in. The area underneath that power curve over a time represents a portion of that electrical bill that you're going to get at the end of the month. What's your electricity bill measured in, right? How are you billed for? Well, you're billed for a product of electrical power used over a time interval. In this case, that would be kilowatts times hours. You can go ahead and look at your electricity bill. If you ask your parents for the utility bill, for 1EQ utilities or whatever, you can even see that it has its own unit there for your charge. It's kilowatt hours, right? That's how we're charged for electrical usage in our homes, kilowatt hours. And that's a product. It's y-axis units times x-axis units. In general, if we have an accumulated change over an interval, that is what a definite integral is. A definite integral represents an accumulated change over some interval. So if we had a rate of change like the rate at which an oil pipe is leaking, and let's say that's measured in gallons per minute. And we have some time interval on the x-axis measured in minutes. Can we anticipate, right? Can we anticipate what the definite integral of that leak rate over an interval would represent? Well, absolutely. Right? What quantity would be represented by the definite integral? That is a product of dependent variable times independent variable. Well, that would be my leak rate in gallons per minute multiplied by my time interval measured in minutes. What in words would that shaded area represent? Right? What in words would that shaded area represent? Nikki? Yeah, the total gallons that leaked over the time interval A to B. And so a definite integral is a product. It's a product of dependent variable units times independent variable units. And we're going to develop several different ways to calculate definite integrals over the course of Unit 5. This is an awesome unit, okay? We're going to get to a lot of real-life applications that calculus is used for, and so I'm super excited about that. Today we're going to introduce one such approximation for a definite integral, and that's the trapezoidal rule. Okay, this is a big deal. The trapezoidal rule always shows up on the AP exam, typically not only in the multiple choice portion, but in the free response as well. And when we look at some real released free response questions as we work and prepare for the actual AP exam, you're going to see how the trapezoidal rule, along with the midpoint rule, has showed up on the several last years of the free response question. So this will be an important thing we want to make sure we're comfortable with. Today we'll work to develop the trapezoidal rule as a means for approximating definite integrals. And you're going to get stamped eligible items today at 4, 6, 12B, and 13B. I did put those on the agenda. We've got brand new cooperative learning groups today. And so we're going to scooch into our cooperative learning groups in just a sec. I'm going to pause the recording and we're going to come back for our closure. We will need a little over 5 minutes for our closure, so we're going to be aiming in about an hour from now, about 11:25. I want to make sure that we come together so we have time for our closure. And we'll do our 4 and our 4 and our 4 and our 4 and 4 and we're over here. So how are we going to do that? So Riley and Brandon, you guys can join and make a group of 5 there since everybody's here today, and that'll be okay for our discussion. All right, so let's go ahead and I'll pause the recording and let's scooch in our groups and get going. After I record your OTLs. Thank you for your help returning their desks to the regular position. I appreciate that. Everybody, let's focus in on our closure then. What does the area between the curve and the x-axis on a velocity versus time graph represent? And don't say it out loud. Let's have a written response from everybody, and then we'll share on the whiteboard. Secondly, the area between the curve y equals f of x and the x-axis over an interval a to b can be approximated using n trapezoids with the formula T sub n. That's representing the trapezoidal rule taken with n trapezoids. And go ahead and write a formula that can be used with a generalized curve f of x on an interval a to b. Let's think about what that would look like. Finally, where delta x is given by what formula using our x's and our a's and our b's and our f's would that look like? You may do this with your partner and then be ready to share.
Distance travel over right? If it's velocity versus time, so what you put this in y
Oh, wait.
Oh, this, I just copied it. Okay.
Yes, it's equivalent to the h height of their Okay, ladies and gentlemen, let's go ahead and share our responses for today's closure. Firstly, great job. Everybody earned their stamps today, so you guys did a nice job working your new cooperative learning groups. In general, what does the area between the curve and the x-axis on a velocity versus time graph represent then? So what does that area represent? Kobe?
The displacement?
Yeah, absolutely. The net change in position over an interval a to b. So the distance traveled on some interval. Over some interval a to b. Please keep in mind that travel could be spelled with one or two L's. I'm all about saving digital ink though. Conserve, reduce, reuse, make less of it. So I'll go with the one version. Number two, the area between the curve y equals f of x and the x-axis on the interval a to b can be approximated using n trapezoids in accordance with the trapezoidal rule. Call it T sub n. I saw lots of people writing with y's, and that's awesome. Right? In our activity, we used y sub 0 for the first function value, the first left side height of the trapezoid, and then two y sub 1s and two y sub 2s up until one y sub n's at the end. I'm going to use my f notation because I've seen that more frequently. So we knew that that formula is given by 1/2 delta x, or simply delta x over 2 times, and we'll grab one of our first function values. I'll call that f of x sub 0, my leftmost function value, and we'll grab 2 of our next function value, and 2 of our next function value, and 2 of, up until 2 of our next to last, and then finally a single of our final function. We'll call it f of x sub n for our final right side. So we've got a single on each end, our bookends, and then we've got double all of ours in between. How come? Well, because this function value represents the right base of one trapezoid, and then also represents the left base for the next subsequent trapezoid. And so each of these middle function values gets counted twice in my formula. Delta x can be calculated exactly using a and b, right? How would we calculate delta x then? Raise your hand if you got that. So what would we calculate delta x? Riley?
The number of trapezoids divided by all the bases.
So
Times 2. Divide, like, if you're using that equation.
oh, don't use that equation. Instead, think about an interval a to b.
Use n times, like the number of trapezoids times the height, so.
We give you the length, b minus a. So if we wanted to get the height of the trapezoid delta x, we could start with the length and do what? Sophia?
Would it be A minus A?
Absolutely. So we take the length, and now you're about there, we take the length of my interval and divide it up into n, all right? Divide it up into n equally spaced trapezoids, so b minus a over n. This is a big deal, so we need to have this formula, right? We'll be using that to get our delta x calculation. Awesome. What questions do you guys have on your closer today? Great, then I'll go ahead and stop the recording, and you guys can continue working on your OTL.